Hello and welcome to our presentation about faster RCNN models. So the goal of our projects was to replicate some results from the paper Faster RCNN towards real-time object detection with region proposal networks in order to answer the following research question, which is how does the backbone architecture of a faster RCNN model affect object detection performance? So we first used pre-trained faster RCNN models and then tried to train the model by ourselves by using Detectron 2, which has been developed by the same authors as the research paper. So typically that's what the model does. So based on an image, it detects object and with various accuracies. So I'm going to talk now about the metric used to evaluate performance of computer vision models, which is the mean average precision metric. But in order to talk about it, I'm going to first introduce you the intersection over union metric, the IOU. So the IOU metric measures the intersection between predicted bounding boxes and ground truth bounding boxes. So the prediction is correct if the IOU, sorry, is superior to a certain threshold, which typically is 0.5 or 0.75. Then the mean average precision measures the accuracy of model in detecting objects and localizing them accurately in an image. So how is it calculated? First, by computing the average precision for each class of object in the dataset. So the average precision is the area under the precision recall curve, which is the graph that shows precision and recall of the model change as detection threshold varies. The average precision for each class is then averaged across all the classes in the dataset to obtain the MAP. So to summarize, the MAP is a single number that summarizes the overall performance of the model in detecting objects across all classes.
So now let's talk about our learning model, the Foster RCNN. So the Foster RCNN is composed of two parts. One part is the RPN and the second one is the fast RCNN. So the goal of the RPN is to give us regions in the image that are susceptible to have objects. So keep in mind that the CNN backbone is the same for the RPN and the fast or CNN module. So let's go through the RPN. We go through the CNN backbone, we get a feature map, then we do a 3 by 3 convolution, then a 1 by 1 convolution to do classification, and a 1 by 1 convolution to do bounding box regression. So here the output of these neural networks is the boxes that are susceptible to get object inside. So after this, we do a proposal pruning. That means we only keep the bounding boxes with the highest probability of having an object inside, and also we remove all the overlapped bounding boxes. So now let's jump on the fast or CNN part. So as we mentioned it before, we have the same CNN backbone, so we have the same feature maps, and then we do scaling and a projection of these bounding boxes into the feature maps. So we just extract these regions here. We have this region here, and we do a normalization. It basically, it's just doing a max pooling over some parts of these regions, and then we just transform this region into fixed length vectors, and this operation is called ROI pooling. So then these fixed length vector are fed into fully connected neural networks, And then we have an other fully connected neural network, one for object classify, one for the classification of the objects, and one for the regression of the bounding boxes. And then the final output of the fast store or CNN is the bounding box that contains objects and then also the label of the objects. Here we have two dogs.
Hello everyone, my name is Aditi Karan and I'll be presenting the experiment design aspect of our project. Uh, for the dataset, we are using the COCO 2017 dataset, which stands for Common Objects in Context dataset. It contains three subsets, that is train, validation and test. Uh, each subset includes images from different categories such as animal, vehicles and people. We use the validation subset in our experiment to evaluate the performance of our object detection model. Our research question is, how does the backbone architecture of a faster RCNN model affect object detection performance? To answer this question, we varied the backbone architecture of our model, specifically using ResNet 50 and ResNet 101, and modified the length of the training schedule. Our hypothesis is that a model with a more complex backbone architecture, that is, a model which has more parameters, will have better object detection performance. We evaluated the accuracy and speed of our model using these architectures. To implement our experiment, we made several modifications to the code. We changed the backbone architecture of our model to ResNet 50 and 101, which are widely used architectures in computer vision. We also adjusted the length of the training schedule to 1 and 3 as described in the paper we based our experiment on. Finally, we used an alternate database because the initial framework was deprecated and selective search couldn't be used. We modified the code to implement these changes and measure the accuracy of speed. Overall, our experiment aimed to explore the impact of the backbone architecture on object detection performance. And by varying the architecture and training schedule of our model, we hope to gain insights into how to improve the accuracy and speed of object detection models. Thank you.
Alright, to summarize our work, we set out to answer the question of whether using more complex backbone models can improve the performance of these networks, and our results are both interesting and promising. We hypothesize that deeper and wider models would be better suited for capturing more abstract and fine-grained features in the data, leading to higher accuracy in the test set. We tested this hypothesis by comparing the accuracy of three different models: ResNet Convid 4 backbone with Convid 5 head, ResNet Convid 5 backbone with dilations in Convid 5, and the ResNet plus FPN backbone. What we found was that the most complex backbone model, ResNet plus FPN, achieved the highest accuracy on the test set over the other models. This suggests that using a wider, deeper model with more efficient scaling and indeed lead to the better performance on image classification tasks. However, we also observed that the simpler models such as ResNet 50 achieved competitive results with accuracies that were not significantly different from the more complex models. This suggests that using a very complex model may not always be necessary or beneficial, and that there might be a trade-off between the model complexity and generalization performance. Furthermore, by comparing the inference times, we observed that ResNet plus FPN backbone with R50 and R101 models achieved the fastest inference times with an average of only about 0.14 to 0.18 seconds per image, while ResNet Convid 4 and Convid 5 backbone has slightly slower inference times, ranging from 0.44 to 0.61 seconds per image. Our results suggest that the choice of model should be carefully considered based on the specific requirements of the task, such as the available computing resource, the size of the dataset, and the desired level of accuracy. Overall, our research has shown us that the using more complex backbone model can be a promising strategy for improving the performance of deep neural networks and image classification tasks. And we hope that our findings will be useful for researchers and practitioners in this field who are looking to optimize their models and achieve better results. Thank you for your attention. Have a good day.